We define the generalized Dirac delta function as a function with the properties delta of t minus t naught equals 0 for t not equal to t naught, and the integral from negative infinity to infinity of delta of t minus t naught dt is equal to 1. We can visualize delta of t minus t naught as the limit as tau goes to 0 of the function d sub tau of t minus t naught equals 1 over 2 tau for t between t minus t naught to t plus t naught, and 0 otherwise. As tau gets closer and closer to 0, so does the interval on which the function is 1 over 2 tau. But also as tau gets closer and closer to 0, the function gets higher and higher. So as tau goes to 0, we get a spike at t equals t naught. We will need to be able to compute the Laplace transform of delta of t minus t naught so we can solve differential equations in which it occurs. But first, we'll start with a generic function f of t and compute the integral from negative infinity to infinity of delta of t minus t naught times f of t dt. Using that delta is the limit as tau goes to 0 of d sub tau, we can rewrite this as the limit as tau goes to 0 of the integral from negative infinity to infinity of d sub tau of t minus t naught times f of t dt. And since d sub tau of t minus t naught is 0 for t outside of t naught minus tau to t naught plus tau, we can narrow this to the integral over that interval, from t naught minus tau to t naught plus tau of d sub tau of t minus t naught times f of t dt. But over this interval, d sub tau is simply 1 over 2 tau, which is constant, so we can bring it outside of the integral, leaving us with the limit as tau goes to 0 of 1 over 2 tau times the integral from t naught minus tau to t naught plus tau of f of t dt. To compute this integral, we are going to need to use the mean value theorem. By the mean value theorem, if capital F of t is an antiderivative of f of t, then there exists some t star between t naught minus tau to t naught plus tau, so that f of t star is capital F of t naught plus tau minus capital F of t naught minus tau, all over the length of that interval, 2 tau. Notice that since capital F is an antiderivative of little f, the numerator of this fraction is precisely the integral of f of t dt when we evaluate from t naught minus tau to t naught plus tau. Thus, we have that this integral is 2 tau times f of t star. So we can rewrite the limit as tau goes to 0 from above of 1 over 2 tau times the integral from t naught minus tau to t naught plus tau of f of t dt as the limit as tau goes to 0 of 1 over 2 tau times 2 tau times f of t star. But 1 over 2 tau times 2 tau is just 1, and this leaves us with the limit as tau goes to 0 of f of t star. Since t star is bound between t naught minus tau and t naught plus tau, as tau goes to 0, we must have that t star goes to t naught. And thus the limit as tau goes to 0 of f of t star goes to f of t naught. And we can conclude that the integral from negative infinity to infinity of delta of t minus t naught times any function f of t dt is given by f of t naught.